Welcome everyone to chapter 2 about limits. So in differential calculus, there's three big tools that we use. First, sine tables of a function. Second, limits of a function. And then derivatives of a function. So we have already covered sine tables. Now we're going to study the big topic about limits. So before we go into the first few definition, the idea here is we start with a point, okay? And typically that point is inside the domain, or is it? Okay, so it's not necessarily inside the domain, so it could be inside or not. Of course, when we have a point inside the domain of a function, what we normally do is we evaluate that function and we study like what is the output of that function. Is it positive? Is it zero or whatever? But the power of the limits here is that we're going to be able to study the function around A without looking at the output. And that's the true magical part of it. So let's go into it. First up, at 2.1, one-sided limits. So again, we have a point. It could be inside the domain or not of a function f, and we want to study that function around that point. And this is really the key word here. It's around. We don't care if A is even defined at A. It could be defined or not, but we're trying to study the numerical behavior / visual behavior of that function around that point. So the first one, or the first definition here, is the left-sided limit. So the left-sided limit, so the first definition here, left-handed or left-sided limit. So here we want to study the outputs of f of x as the inputs are getting closer to A, but the word left-handed here means that we're going to look at outputs that are strictly less than A. So if the outputs of f of x becomes very close to a number L, as the input approaches A from the left, so from the left simply means that the x's are less than A, then we say that L is the left-handed limit of f as x approaches A from the left. And this is denoted by limit, so I'll just put this here, so as the limit as x approaches A minus. So the A minus here is really, really important because it really illustrates that we're approaching it from the left. So lim means like what's going on with that function. X approaches A minus as the inputs are approaching A, but with inputs slightly less than A of f of x. And if these numbers are getting closer and closer to L, we say that the limit of that function as x approaches A from the left is L. If it does not get closer to a number, if it just gets bigger and bigger or smaller and smaller with no upper or lower bound, or it just oscillates between different numbers, then we say that the left limit does not exist. And many times I'll be referring like to the left limit simply as x approaches A minus. So sometimes I just simplify the notation and I just use x approaches A minus. So that's for the left limit. And again here, just a quick remark, I'm reading these definitions. There's a lot of notation and terminology, but we'll be computing this together. We'll be labeling this together on graph, and we'll be computing this together later. The next definition is the right-handed limit or the right-sided limit. So here it's very similar to the left limit. So we're looking at the behavior of the function for inputs getting closer to A, but now with numbers that are slightly bigger than A. Okay, so the right-handed terminology here is really you're on the right side, so the numbers are bigger on the right side. So if the outputs of f becomes closer and closer to a number L as the input x approaches A from the right, so right simply means that the inputs are bigger than A, then we say that L is the right-handed limit of f of x as x approaches A from the right. And the notation for that is the limit as x approaches A plus of f of x is equal to L. So that's the notation for the right-handed limit. And again here, the difference between the left and the right limit is that x approaches A plus. So it's very subtle here. but there's a difference in notation between the plus and the minus here. And again here, when I'm going to refer to this quickly, I might just say, hey, let's study what happens when x approaches a plus simply. So this is really where all the information is. Okay, so that's the right-sided limit. And again here, if it does not go anywhere, okay, we simply say that the right-hand limit does not exist. So we use DNE, of course, that's the short form for does not exist. There's actually a lot of ways of how a limit would fail to exist. And depending on how it fails, sometimes we use different notation and we don't just use the DNE notation for so DNE is like it's like a big umbrella of like all possible shit that could happen with a limit. But inside that realm, there's specific things that can happen. And if you can identify why a limit fails to exist, you need to use that notation. The first symbol is infinity. When are you going to use the infinity symbol? Well, if you're computing a left or right limit and the output are just getting bigger and bigger with no upper bound, then we're going to say that the limit is equal to infinity. Of course, this is not philosophy where we're trying to debate, like, does infinity exist in the vacuum of space or whatever? Like, I don't care about that. If you're computing outputs and they get bigger and bigger with no upper bound, you just say that the limit does not exist because it goes to infinity. So we just summarize that with equal to infinity. Of course, it's possible that the outputs are just getting bigger and bigger, but negatively speaking, so then we're going to say that the limit of that function, left or right here, is going to be equal to infinity. And if you're trying to compute outputs of a function for points on the left side or right side where the function is actually undefined. So of course there's no limit. The limit does not exist because the function is undefined. So there's a distinction here between does not exist, infinity, minus infinity, and undefined. And hopefully with the examples, we'll clarify the distinction between these notations. So if a limit left or right, so that's for the next definition here, and this links with something that you should know from looking at a graph. You should be able to identify vertical asymptotes. You know vertical asymptotes from two functions, like 1 over x has a vertical asymptote at x equals 0, or ln of x also at x equal to 0. So if a one-side limit goes to infinity, doesn't exist because it goes to infinity or minus infinity, then we say that this function has a vertical asymptote at x equal a. So that's one way to compute if a function has a vertical asymptote if you don't see it. All right, let's do an example. So we have a function g, and it's defined visually by a graph. So the first thing is we're going to just review how to compute outputs for the function g at 0, 2, and 5. So what I've done for us here is I've created a table where I have my inputs 0, 2, and 5. And I'm just going to first compute the output. So I have my inputs. Let's compute the outputs of that function. So it's just small review here, making sure that we understand how to compute outputs from a graph. Okay, so you should be very familiar with that. So at 0, so the first point here, I can see that my output is up here at 2.5. So at 0, my function is equal to 2.5. The next point is 2. When I look at my graph on top of 2, I just see 2 hollow dots. I don't see any full dots. So the function is undefined at 2, so UND. And then at 5, on top of 5, I have a hollow dot, but I also have a full dot. And the height of the full dot here, it looks like it's slightly bigger than 1. I'll just use 1.25. So this is just evaluating the function at 0, 2, and 5. Now the new stuff. So now let's compute the left limit, and we'll do the right limit at the same time. Okay, so here I've created a column for us for the left limit. So here's my column for the left limit, and I have also a column for the column for the left and then a column for the right. So I have a column for the right. I'll show right here. Okay, so let's compute left and right limit for 0, 2, and 5. So the idea with left and right limit is you're approaching, it's like you're pinching. So you're on the graph. So for example, at 0, what is the left limit? Well, if you are on the graph and you're getting closer to 0 from the left side, you're getting closer to the output. So here, as you're approaching 0 from the left, you're approaching the full dot that is at 2.5. So the left limit here is 2.5. And then from the right, so if I'm just drawing the graph from the right, getting closer to 0, I'm going to get to the full dot again. So the right limit is also 2.5. So here, left limit, so looking at outputs, like using points that are getting closer to 0 on the left side or the right side, we're getting closer and closer to 2.5. So it's kind of a boring example here because the function is actually continuous there, but we'll talk about this a bit more. Let's just focus on the limit. So now around 2, this is like the fun part now because there's no output at 2, but you can approach 2 from the left side. And if you're looking at the function approaching 2 from the left side, you have output. So if I'm looking at this arrow, if you take inputs that are getting closer and closer to 2, the outputs are going to get closer and closer to the white dot, and the height of the white dot on the left side is 3, so the limit is 3. So limits is like this tool that allows us to capture that white dot, because of course if you evaluate the function, there's nothing, it's undefined. But as you're using inputs close to 2, like 1.9, 1.99, you're going to get outputs that are very, very close to 3 and getting closer and closer to 3. And then on the right side, so if you're on the graph here and you're approaching 2 from the right side, so using inputs like 2.1, 2.111, you're going to get closer to the other white dot, where the height of that white dot is 1, so the right limit is actually 1. So as you're approaching 2 from the left, you're approaching the white dot that is at 3, where the y value is 3, and as you're approaching x equal 2 from the right, you're approaching the white dot where the height of that white dot is 1. So really the limit is those hollow dot calculator that we could not really get by simply evaluating the function. The next example is also interesting, what's going on around 5. So we know the output at 5 is 1.25, but what about the limit? So here, if you pick values very close to 5 on the left side, so I like to illustrate this with arrows, you're going to approach what? You're going to approach the white dot. And the height of that white dot on the left side is of course 2. And here, if you are using inputs slightly bigger, like 5.1, etc., your function is going to get closer to the white dot again, the same white dot at the same height. So the value is going to be equal to 2. And I don't want to confuse you guys, but I find once you know how to compute left and right limit, might as well talk about the two-sided limit, because the two-sided limit is basically check on the left, check on the right. If it's the same thing, then your answer is that number. But as soon as they are different, then you say that the two-sided limit does not exist. So here, we have a brand new, and I'll go over the definition in a second, but I just want to look at it. So this column here is for the two-sided limit. Okay, so this is coming from example 2.2.2 after the introduction of the definition that we'll go over right now. So, but I find logically here it's not too difficult. So the two-sided limit, which is basically trying to compute how is this function behaving around a left and right at the same time. And the idea is that if they are the same, then you just put that number, but as soon as they're different, so they don't behave the same way, you just say that the two-sided limit does not exist. So it's really just a logical comparison game. So if you are computing the two-sided limit around 0, because we have 2.5 on the left side and 2.5 on the right side, you get again 2.5 for the two-sided limit. So you get 2.5 again, but around 2, we have 3 on the left and we have 1 on the right. As soon as they're different, does not exist. Okay, so that's the right answer. What about around 5? Well, it's 2 on the left side and 2 on the right side. So the limit around 5 is 2 again. Okay, so two-sided limit, very, very straightforward stuff. Actually, let's go down there. So let's just scroll down, okay, all the way to the section 2.2. Might as well talk about that definition because it's fairly straightforward. So what are two-sided limits? So to some extent, two-sided limits are nothing new. So the definition is very, very straightforward. So if you compute the left limit and you compute the right limit and you get the same thing on both sides, and this could be both sides are infinity, both sides are minus infinity, or etc., then you say that the two-sided limit is equal to a. And as soon as they're different, so you check left and right, they're not the same, then the two-sided limit does not exist. And we just did example 2.1.5 together, just comparing the left and the right. Actually, what I want to do is finish that example 2.1.5 just to give you like a full of understanding on how we can ask you limit questions on a graph. So when we give you a graph, we can compute outputs from the graph. We can compute left-sided limit, right-sided limit, or two-sided limits. And again, two-sided limits is just check left and right. Are they equal? If so, boom, you're done. If not, does not exist. But also what we can do is study the behavior of the graph for large inputs, positive or negative. And those behaviors are going to be captured through limits at the infinite. So let's go to the definitions in 2.3. Let's talk about limits going to infinity because it's very similar. And this will allow us to really do everything, like every example that you get. You know, if I give you a graph, you can do everything. Left, right, two-sided, and limits at infinity. So the next definition in 2.3, limits going to the infinity. So here, the first definition is what is a limit to infinity? Well, here the idea is that if the outputs of f are getting close to a number L, as the inputs gets bigger and bigger with no upper bound, then we say that the L is the limit to infinity of the function f of x, and the notation for that is lim of x goes to infinity, f of x is equal to L. So that's my, so here we go. So boom. Okay, so that's my, wow, what? Here we go. Boom. No. Here we go. Boom. Here we go. Here we go. Boom. Okay. And voila. So, and of course, if the function does not go to a specific number, we will say that the limit does not exist. So this is for going to infinity. And again, here I will sometimes just refer to this as, okay, x goes to infinity. This is just like a shortcut notation. What about minus infinity? So on the other extreme. So again, same sort of idea, a lot of words here to really try to seize a fairly simple concept. So if the outputs of the function gets closer to a number L, as the input gets larger, but negatively speaking with no lower bound, then we say that L is the limit to minus infinity. And this is, of course, denoted as lim, as x arrow to minus infinity is equal to L. And of course, if it doesn't go anywhere, so to a real number, we just say that the limit does not exist. And again, just like one-sided limit, sometimes we can explain why the function does not have a limit going to infinity or minus infinity. If the function just goes up forever, okay, then you just say that the limit is equal to infinity. If the function goes down forever, then you say the limit is minus infinity. And there's a link, a visual link that you can make when you are computing a limit to infinity or minus infinity. If you're getting a number, then this means that the function is approaching an horizontal line, and that horizontal line, y equal L, will be the horizontal asymptote. So if you're computing a limit to infinity and you get L, or the limit to minus infinity and you get L, you say that y equal L is an horizontal asymptote. So what we're going to do is we're going to go back to that example 2.1.5 and we're going to compute the limit to the infinities of that example. So let's scroll up. All right, if we are going back up to the example 2.1.5, now let's compute on that function the limits going to the infinite. So limit going to minus infinity and the limit going to infinity. So for the first one, boom. Okay, let's compute the limit as x goes to minus infinity. How do we do that? So here, it's really important when you have a graph in front of you, if there's no full dot at the beginning or at the end, this means that the graph will continue forever with the same shape. So here what I can do is kind of extend the graph. So I'm trying to study what's going on to minus infinity. So if you look at this graph, it will just go down forever. So this function is always increasing concave down if I'm using calculus term. So here, so if you extend, poof, okay, the graph, you see it will go down forever. So since it's going down forever, so here we go, boom. Okay, so if it goes down forever and it's not approaching any horizontal asymptote or anything, so you can see that this function will just go in hell to minus infinity. So this means that the limit as x goes to minus infinity is minus infinity. This function goes down forever. So for very large x's, negatively speaking, the function will go down forever. What about the limit to infinity? So you just go on the other side, the other extreme right here. So let's compute, poof, the limit going to infinity. Well, if we are computing the limit going to infinity, it would be good to extend the graph so that we can understand carefully its behavior. So poof, so if you extend here the graph of this function, so you see that this function is again going to go down forever. So for very large x's, the function goes down forever. So it's going in hell again. So boom, okay, so minus infinity. So if you are computing the limit as x goes to infinity, you're going to get again minus infinity. So minus infinity. So here on both ends, so for very, very large x values, negative values, so for very, very large x values, my function goes down forever to minus infinity. For very large, negative x values, and then for very large positive x values, my function is again going down forever to minus infinity. So these limits to the infinite, they're really describing what's going on outside the box of the graph here. So if you go on forever to minus infinity, the function goes down forever to minus infinity. If you go up forever to infinity, the function goes down again to minus infinity. And this is everything we can do on a graph. So computing domain, labeling domain, labeling range, checking where it's continuous. And maybe this is a good way to tie up something with continuity here. You can notice, for example, just a quick remark. It's not really the point of this chapter. It will be the point of the next chapter. But you can notice, for example, that my function is continuous around 0. So you see it's continuous. You can draw it without lifting your pen. And how can we see this using the limits? Well, if you look at the limits, the output, the left, the right, and the two-side limit are all equal. Meanwhile, obviously, if you are around 2, the function is not continuous at 2 because it's not even defined. But you can see this also in that table that there's no output, it's undefined, and the left and right limit are not the same. What about 5? Because 5 is in the domain, but even if 5 is in the domain, you need to lift your pen to draw that dot down there. How do you see this in the table? Well, you see this in the table because the output, which is 1.25, is not equal to the left, right, and two-side limit. So as the only way a function is continuous is when everything is equal, output, left, right, and two-side limit. As soon as one of them is different, the function is no longer continuous. Remember that because we're going to spend a full chapter on this in chapter 3. All right.